All right, the final part of this post-lab analysis is calculating the activation energy. This is a sort of a version of the Arrhenius equation. So rate constant K1 at T1 and rate constant K4 at the higher temperature at T4, 35 degrees. So we can calculate EA knowing our gas constant R. So a couple of things here, some constants that you need to acquaint yourself with are, and I'll give all of these on exams, the constants. It's going to be for R in this Arrhenius equation, we'll take the form of 8.314 joules over mole Kelvin. So T4 is 35 degrees C. Okay, that is what we did in our water bath. If you saw the definition, if you saw our demonstration, excuse me. Let's put that in Kelvin because R is in Kelvin. So let's add 273 to that and see what we get. I'm getting about 308 K. And our other temperature that we did was at 24.5 degrees. So at 24.5 degrees, we'll go ahead and convert that to Kelvin. Okay, so we got T1 here, we got T4 here. What is K1? And so K1 is something that we solved here. Since they have the same conditions, experiment 1 and experiment 4, the only thing that's different is one is done at a higher temperature. The K1 value is 0.00679. So let's put that in here sort of as our inventory. And K4, which we just calculated in our previous problem, is 0.0147 m to the minus 1 second to the minus 1. Okay, so this is at one temperature, 35. This is at 24.5. We can solve for EA. Activation energy is an energy, so it's going to probably be in joules. Actually, I'm thinking it's going to be joules per mole. All right, let's put in our numbers here. K1 and K4 equals EA, that's what we're trying to solve for, divided by 8.314 joules divided by mole Kelvin, and really causes that to flip. But we'll just say joules divided by mole Kelvin times 1 over T4, which is 308 K, minus 1 over T1, which is 297.5 K Kelvin. All right, this is a mathematical mess, but we can break it down. So let's go ahead and break this down. First thing I'm going to do here is I'm going to solve for this, and whatever that messy number is, I'm going to write it down on the piece of paper. So 0.00679 divided by 0.0147. And let's take the natural log of that fraction, natural log of the answer. And a crazy number here is minus 0.7724. I'll just put in some extra digits there. Minus 0.7724. Okay, that's good. I'll leave that alone. Now I'm going to solve this 1 over 308 minus 1 over 297. And then I'm going to divide it by 8.314. Okay, so 1 divided by 308 minus parentheses 1 divided by 297.5, close the parentheses. Okay, get that number. Okay, I'm going to okay, so that subtraction is equal to that. I'm going to divide it by 8.314, which is the constant, and we're getting really some messy numbers here. So 1.378 times 10 to the, I think that's minus 5, 4 zeros, so it makes it minus 5. That times EA, so don't forget the EA there, right? So this we figured out divided by that, the EA stays there, and the units here, well, I'm going to put the units at the end. The units are going to be joules per mole, so we'll just make my life a little bit easier here. This minus sign cancels out with that minus sign. So the EA here, the activation energy, I already know it's in joules per mole, is going to be 0.7724 divided by 1.378 times 10 to the minus 5. And don't forget to put your units back in the end. So if you want to carry the units, this joules per mole in the denominator flips. This Kelvin's cancel out with that Kelvin, and it's actually going to be moles over joules. But then when we solve for EA, this joules goes here and the moles goes down there. Okay, so really my units correlate, right? So EA, this joules over moles flips, and then moles over joules, and then solving for EA, the joules goes here, and the moles gets divided here to isolate EA alone. Anyways, let's solve for that. 7724 divided by parentheses 1.378 times 10 to the power of minus 5, and getting about 56,052 joules per mole. Let's divide it by 1,000 to get it as 56.0 or 56.1 kilojoules per mole. And that's going to be our answer for the activation energy for this reaction of the iodine clock. Now, finally, your last post-lab question has to do with the effect of the catalyst. So for that, we're going to have to look at the catalyst. The catalyst in this reaction was copper sulfate. All right, so again, 5 had the same conditions as experiment 1. Experiment 1, we had the reaction proceed with a color. It went to completion at 167 seconds. With the copper sulfate drop, it completed at 25 seconds. So we need to figure out the rate 5 divided by rate 1, which we've already calculated. Rate 1 here, let's go back to our concentration table. Okay, rate 1 was this. Now we need to figure out rate 5, which is the rate that happens in the presence of the copper sulfate. So let's go ahead and quickly do that.